When you write software for a single computer, the rules are comforting and predictable. The environment is deterministic. If the hardware is working, the same operation will always produce the exact same result. And if the hardware breaks, the consequence is usually straightforward. The entire system simply stops. You get a kernel panic or a blue screen, and everything shuts down cleanly. If that single computer gets overloaded, the traditional response is to buy a bigger machine with a faster CPU and more memory. But eventually, you hit a hard physical and financial ceiling. High-end machines become prohibitively expensive, and there are limits to how much processing power you can physically cram into one box. The solution is horizontal scaling. Instead of buying one massive supercomputer, you string together dozens, hundreds, or thousands of smaller, cheaper commodity machines to share the workload. Confining your application to a single machine severely limits how much traffic you can handle, but it gives you an incredibly valuable guarantee: a reliable, predictable environment where every command executes exactly as written. When you link those smaller machines together, you move into what engineers call a shared nothing architecture. These individual nodes don't share memory or disk space. Their only way to coordinate is by sending messages over a local network. That network introduces a massive new variable. You can no longer assume that communication between two parts of your program is instantaneous, or even that a message will arrive at all. This leads to a problem known as partial failure. In a cluster of 1,000 computers, one specific node might stall, run out of memory, or simply die. Meanwhile, the other 999 nodes keep running, completely unaware that their neighbor is gone. Because of these partial failures, the entire system becomes non-deterministic. The exact same operation might execute perfectly one second and inexplicably stall out the next, depending entirely on the unpredictable status of the network or a specific machine. You are no longer controlling a single, predictable brain. You are managing a chaotic ecosystem where localized failures are a mathematical certainty. To see how this plays out, let's look at a standard e-commerce architecture. This diagram shows a network of independent microservices handling different tasks, like payments, inventory, and notifications. A user clicks Buy, which prompts the payment service to process the credit card and send a reservation request across the network to the inventory service to secure the item. But the network is an asynchronous packet system. If a router is misconfigured or a switch gets overloaded, that data packet can drop mid-transit. This exposes a paradox of asynchronous networks. The payment node sent the message, but it didn't get a reply. And if the node doesn't receive a response, it physically cannot know what happened to its request. The silence could mean 3 different things. The initial request might have been lost in the network. The inventory node might have crashed right as the request arrived. Or the inventory node processed the request perfectly, but the confirmation response was lost on the way back. To the payment service, all 3 scenarios look identical: a blank screen. A lack of response provides 0 usable information, trapping the originating service in a permanent fog of war. The standard engineering solution for this silence is a timeout. The payment service waits for a specific number of seconds, gives up, and assumes the inventory node is dead. But a timeout is just a guess. It cannot distinguish between a machine that has actually crashed and a machine that is functioning perfectly but is stuck behind a congested network queue. When the timeout hits 0, the system's automated reflex is to simply try again, firing off a duplicate request to the inventory node. If the inventory node was just running slow, that original request was already processed. The lost confirmation finally limps back to the payment node right as the blind retry is sent out. Now, the inventory node receives the exact same instruction twice. The final business result is a disaster. The customer gets charged twice for the same order, and the warehouse database deducts an item that doesn't exist. And this danger scales rapidly across the network. If the network is already congested, having every impatient node suddenly spam blind retries will overwhelm the remaining active servers. This creates a feedback loop that can take down the entire data center. If a local app fails, you just hit refresh. But applying that single machine logic to a complex network creates data corruption and accelerates system collapse. Engineers cannot fix the network. Unbounded delays and dropped packets aren't software bugs. They are inescapable physical realities of laying heavy cables across oceans and routing data through thousands of switches. Success in distributed systems requires a different mindset. You stop trying to perfect the communication channel and instead focus on building reliable software out of inherently unreliable components. To safely handle the danger of network retries, engineers use a concept called idempotence. An idempotent operation is a task that can be performed multiple times, but will only ever apply its effect once. When the payment service sends its request, it attaches a unique transaction ID. If the inventory node receives a duplicate retry, it scans that ID, recognizes that it already completed the task, and safely discards the message without double deducting the item. In a single computer, you write code assuming it will work as intended. In a distributed system, you must write code assuming every component is already broken.